All right, so we want to prove some properties about isomorphisms here. And in a nutshell, the properties in these two theorems, theorem 6.2 here and theorem 6.3 here, summarize certainly the main things you should know about isomorphisms as far as what they preserve. They really end up preserving all the abstract group theoretical properties between two given groups that happen to be isomorphic. They are the same group up to isomorphism. They may look different, they may be represented differently, but they have the same algebraic structure to them. First property here is that phi carries the identity of G to the identity of G bar. The book's proof of this is really what you might call slick, and I probably wouldn't have thought of it right away. Using the fact that E equals E times itself, the identity in G, you can replace phi of E with phi of E times E, and then use the operation preserving property to say that's phi of E times phi of E. But we also know that E bar is the identity in G bar, and therefore this equation is definitely true because E bar is the identity in G bar. And so then you get equality between these two things here and here, and you can do a right cancellation, say, of the phi of E's, and say that phi of E on the left there would equal E bar on the left there. And that would be kind of a slick proof of the fact that phi of E is E bar. Phi sends the identity of G to the identity of G bar when phi is an isomorphism. My thought about proving this was not quite so slick. It's a little bit more cumbersome, but it does technically work. My thought is, okay, give me an arbitrary element in G bar, show that if I multiply it by phi of E, that I get G bar back. That was my thought. Then phi of E would have to be the identity E bar in G bar. Then the question is what to do, or how do you actually do that? Well, hopefully a little bit of thought. Excuse me, if you took this approach, it reveals that, well, since phi is an isomorphism, it's also onto. So for this given arbitrary element of capital G bar, there would have to be something in G that gets mapped to it. Something in capital G that gets mapped to it, call it little g. I'm not writing a proof here. You'd say something like, since phi is onto, there exists a little g in capital G such that G bar equals phi of G, and therefore you can write this. Then when you see something like this, I hope you're starting to feel you're at the point where it clicks that, hey, I better use the fact that phi is operation preserving to write this like this. But now, hey, wait a minute. E is the identity of G, and therefore this equals phi of G, which I've already said is equal to G bar. So now I have it. G bar times phi of E equals G bar. Phi of E is an identity, and in fact, you know the identities are unique. Therefore, phi of E must be E bar. That was my thought about how to do this. Not quite as slick as the book's approach, but it does work. Does that make sense? Is there anything I can clarify about that? About the approach you thought of? Nod or shake your head or no? Don't want to answer? That's what I thought of. The next property, showing for every integer n, phi of a to the n equals phi of a to the n power. I said, just go ahead and do this for positive integers, and I hope you found this one fairly straightforward, fairly easy. Using induction, well, the n equals 1 case, the base case, as it often is trivial. phi of a to the first is phi of a is certainly phi of a quantity to the first by definition of what it means to raise something to the first power. The inductive step would be to say, assume phi of a to the n equals phi of a quantity to the n for some positive integer n in the natural numbers, also called the positive integers, and show that if you replace n with n plus 1, that it still works. And yeah, it's not too hard. Phi of a to the n plus 1 by definition is phi of a to the n times a. Since phi is operation preserving, that's the same as phi of a to the n, and that's times phi of a. Phi is operation preserving. And now use your inductive hypothesis. That's the same as phi of a quantity to the n. Inductive hypothesis, which is by definition phi of a to the n plus 1. And then you'd say, as usual, by the principle of mathematical induction, this means this is true not just for some n, but for all n, right? The inductive hypothesis, you're assuming it's true for some n. That's a common thing to forget in your inductive proof, is to emphasize that's true for some n in the inductive hypothesis, but at the end, you end up saying, by the principle of mathematical induction, it's true for all such n. That's the point. So that proves it for positive integers n. Then I go ahead and think about it when n is -1. It's also true when n is -2, -3. It's also true when n is 0, because by definition, raising something to the 0 power, it gives you the identity. Why is it true when n equals -1? I want to show phi of a inverse equals phi of a inverse. I'll put a question mark there. Well, you'd want to show that when you multiply this thing times phi of a, you get the identity. That would mean it would be the inverse of phi of a. So do that. Multiply phi of a and phi of a inverse. As always, you got to use the fact that it's operation preserving. And here we can use property 1 that we proved a few minutes ago, that E gets mapped to E bar under an isomorphism. So you've got the product of these two things being the identity in G bar. Therefore, phi of a quantity inverse is this thing right there, phi of a inverse. Since inverses are unique, if you want to emphasize that. Property 4 was to prove that if, well, G equals the cyclic subgroup generated by A, if and only if, IFF, G bar is the cyclic subgroup generated by phi of A, which would prove that G is cyclic if and only if G bar is cyclic as well, which is a property on the next page. I said to try to do a little extra careful proof of this one. It's an if and only if, so that means there's two directions to prove, and it's possible the arguments are not completely symmetric unless we are going to refer to the inverse isomorphism, but let's just do it as if we haven't thought about the inverse isomorphism at all. Suppose G is a cyclic group generated by some element A. You're trying to show that G bar equals the cyclic group generated by phi of A. Certainly, listen carefully, certainly this set that I'm pointing at right now is a subset of that set. Certainly, I'll write it this way. The cyclic subgroup generated by phi of A is a subset. You could even say a subgroup of G. I'll just write it as a subset. We're trying to show two sets are equal. When you look at this equation, you should say that's an equality between sets. G bar, thanks. That's an equality between sets. So to show two sets are equal, show one is a subset of the other and vice versa. Certainly that's true because, I mean, all the elements in here are in G bar to begin with, by definition. So the only question is, are all the elements in G bar in there? Given little g bar in capital G bar, is it a power of phi of A? Hopefully you're at the point where this kind of thing clicks that you can all you need to do is use what you're assuming. I mean, and you have to use that. There's no other way to do it. We need to use what we're assuming there, that all the elements of G are powers of A, and use the fact that phi is an isomorphism. You can say that implies there exists a little g in capital G such that phi of G equals G bar. You can even say emphasize it's unique if you want, but the uniqueness is not necessary. But little g being in capital G means it's a power of A. Probably should have written this to begin with. Therefore, little g equals A to the n for some integer n, and we can then say phi of A to the n equals G bar. I'm being a little bit more wordy perhaps than I absolutely need to be. I probably could have jumped right to that line without this intermediate line, but I'm being a little extra thorough. But hey, phi again is an isomorphism. It's operation preserving. We already proved that phi of A to the n is phi of A to the n by property 2 that we already proved. Partially proved. We didn't prove it for n is -2, -3, etc. But that is the case. In other words, G bar is a power of phi of A. Therefore, G bar is in the cyclic subgroup generated by phi of A. And since G bar is an arbitrary element of capital G bar, therefore capital G bar is a subset of the cyclic subgroup generated by phi of A. And combining those two things, this one and this one, means they're equal. G bar equals the cyclic subgroup generated by phi of A. What about the other direction? It is possible to think about this in terms of the inverse isomorphism, which does exist, and we proved before the test, in fact, that it's operation preserving. You might remember last Friday. But let's try to do it without referring to that. Suppose G bar is equal to the cyclic subgroup generated by phi of A. Just like before, there's a certainly, we can say certainly the cyclic subgroup generated by A is a subset of G. Again, the harder part is showing G is a subset of the cyclic subgroup generated by A. If I'm not referring to the inverse isomorphism, how is this possible? Is it possible? Yes. Let G be in capital G. My goal is to show little g is a power of A. Right? That'll mean it's in the cyclic subgroup generated by A. Using the fact that phi of A generates G bar, okay, I've got to use that fact. I got to use what I'm assuming. Just write it this way. Then there exists an integer n such that phi of G equals phi of A to the n. I know G bar, I'm assuming G bar is generated by phi of A. I know that phi of G is in G bar. Therefore, it's got to be a power of phi of A. But phi of it, phi is operation preserving. This is the same as phi of A to the n. Am I done? Does that do it? Does that prove that G is a power of A? What other fact about isomorphisms do I need to get to my final conclusion? That evidently G would be A to the n. I can conclude that, but I should mention one other property that I'm using to get that conclusion. It's 1-to-1. Phi is 1-to-1 now implies G equals A to the n. G is a power of A. An arbitrary element of capital G is a power of A. So it's in the cyclic subgroup generated by A, and therefore G is a subset of the cyclic subgroup generated by A. And combine these two things, and you'd say G equals the cyclic subgroup generated by A. I mean, the one inclusion here is, again, it's so clear, it's so obvious, so certain that it's even hardly worth mentioning, but just for extra emphasis, I'm mentioning it. The real key thing is proving that. So your first exam went through the beginnings of chapter 6, and these are things you should have been able to prove on the exam, the first exam. I didn't put these particular things on the first exam, but they're of a level that you should have been able to do them if I had. Could be in the second exam, something like this. So second exam you could effectively think of as also starting in chapter 6, whereas the first exam ended in chapter 6. How far will we get? I'm not positive. Certainly through chapter 10 before the next exam. We'll do a very light treatment of chapter 11 because chapter 11 is a pretty hard chapter. We'll just emphasize the main facts of chapter 11, and then we'll move into chapter 12. My guess is we'll get to chapter 12 or 13 before the next exam. And of course, it'll be after spring break in April sometime. I think early April. Okay. Instead of proving the rest, let's just glance at the rest of these facts. These are facts that you should try to remember to some degree. Not that you would have to state this entire theorem on an exam, but you should be able to identify true, false answers and multiple choice based on these. 5 is pretty important. Isomorphisms preserve orders, including infinite orders if the order is infinite. That's a pretty key fact that is maybe more easily forgettable than the other facts. I guess I forgot to do the number 3 there, that they commute. A and B commute if and only if phi of A and phi of B commute. Hopefully you didn't find that one too difficult. 6, when you're solving an equation like this, the number of solutions is equivalent to the number of solutions of an equation like this. The same. X in these equations is an arbitrary variable, an unknown, you might say. It's not a particular group element. That's why they're writing X in both equations, one equation in G and one equation in G bar. X is an unknown that you're trying to solve for. You can solve equations in groups. Look for solutions. If G is finite, then G and G bar have exactly the same number of elements of every order. Same number of elements of order 2, 3, 4, etc. Of course, they have the same number of elements of order 1. That would be true even without thinking about the concept of isomorphisms. And in fact, of course, they don't even have to be isomorphic for that to be true. And then these properties, as we talked about last Friday, the inverse function is an isomorphism. The only thing left to prove is that it's operation preserving. It's definitely one-to-one and onto from what we knew from back in chapter 0. G is abelian if and only if G bar is abelian, and that would be equivalent to also saying G is non-abelian if and only if G bar is non-abelian. G is cyclic if and only if G bar is cyclic, which is equivalent to saying G bar is not cyclic if and only if G bar is not cyclic. As you had in the exam, the direct image of a subgroup is a subgroup. The direct image of a subgroup of G bar under phi inverse is also a subgroup of G. And you remember what Z of G stood for? Not the centralizer, but the center. C of A, the centralizer of an element, is the set of everything that commutes with A. Z of G, the center of a group, is this set of elements in G that commutes with everything in G. The center is the intersection of all the centralizers. There are many centralizers. Their intersection is the center. But phi maps the center of G to the center of G bar. There are actually other things you can say besides these things, but these are sort of the most fundamental properties at the moment. Okay, so you want to kind of just feel like you understand isomorphism so well and that you've worked with it enough that these things are just automatically there when you need them. And they are saying that G and G bar are effectively the same group. They act the same. Their algebraic structure is the same. Properties are preserved by isomorphism. The rest of the chapter, perhaps you might say, gets even harder, talking about automorphisms and inner automorphisms, and this fact here that is called the group of automorphisms of Zn is isomorphic to Un. What are automorphisms and inner automorphisms? Well, the concept of an automorphism is trivial if you know what isomorphisms are. An automorphism is an isomorphism from a group to itself. An automorphism is an isomorphism from a group to itself. There are more morphisms even besides isomorphisms and automorphisms. We're going to see later on that there's something called a homomorphism. And you can also specialize to what are called endomorphisms and epimorphisms. Lots of fun names. That's all it is. Any isomorphism from a group to itself is also called an automorphism. Of course, you can also call it an isomorphism because it is an isomorphism. So one-to-one and onto mapping from a group to itself that is also operation preserving. Think of an example of an automorphism? Sure. If I take phi going to make a simple example here, from Z3 to itself, defined by phi of 0 equals 0, phi of, well, okay, 1 equals 2 and phi of 2 equals 1, that's an automorphism, turns out. It's an automorphism. It's in what we call aut of Z3. And actually, I was thinking to myself as I was defining this, I also could have mapped phi of 1 to 1 and phi of 2 to 2. I could have mapped everything to itself. That would be the identity isomorphism. The identity mapping from a group to itself is always an isomorphism, therefore it's always an automorphism. Maybe I should write that as ID. ID from Z3 to itself maps every element to itself. And it is an isomorphism. It's operation preserving, which makes sense. So therefore, it's an automorphism of Z3. It's also in the set of all automorphisms of Z3. Are there any other elements in odd Z3? No, there aren't actually. And that's based on the fact that, based on these theorems that we were just looking at, well, Z3 is cyclic. Any isomorphism from Z3 to itself, in other words, any automorphism of Z3, has to map a generator of Z3 to another generator of Z3, because it's got to preserve orders. So whatever one gets mapped to, it's got to be mapped to a generator of Z3. Well, the generators of Z3 are 1 and 2. So don't map it to 0, map it to 1 or 2. ID maps it to 1, and this phi here maps it to 2. And since isomorphisms and automorphisms are 1 to 1 and onto, if I map phi of 1 to 2, I can't map phi of 2 to 2. It's got to go to something different, 1. Same kind of argument down here. In fact, these are the only two isomorphisms from Z3 to itself. They're the only two automorphisms of Z3. Sorry. And turn off notifications, right? These are the only two automorphisms of Z3. There's no others. Would these two functions form a group under function composition? They do. In fact, odd Z3 or odd of any group, the set of automorphisms of any group is always a group under function composition. What would be the Cayley table? I hope it makes sense that ID is the identity element of this group. The only question is, what is phi composed with itself? Phi squared, if you will. But the squaring is for function composition, not a literal squaring in the usual sense. Well, what does it map 0 to? Obviously, it maps it to 0. What does it map 1 to? Less obviously. it maps it to 1, but the intermediate steps need to be shown, something like that. What does it map to? It maps it to 2, but the intermediate steps need to be shown like this. Yeah, phi squared composed with itself, or phi composed with itself, which we can call phi squared, maps everything to itself. It is the identity map. In other words, odd Z3 is a 2-element group whose Cayley table looks like this. That's isomorphic to Z2, right? Odd Z3 is isomorphic to Z2, which also does happen to be isomorphic to U of 3, the group of units under multiplication mod 3, positive integers relatively prime to 3, positive integers less than 3 and relatively prime to 3, whose Cayley table looks like this. And there's an example of the more general fact in the book that in general, the group of automorphisms of Zn is isomorphic to U of n, which is not necessarily always cyclic. This example happened to be cyclic. In fact, any group of order 2 has to be cyclic, right? We talked about that a few weeks ago. Any group of order 1 has to be cyclic. It's got to be the trivial group. Any group of order 2 has to be isomorphic to Z2. In other words, it must be cyclic. Any group of order 3 has to be isomorphic to Z3. Any group of order 3 has to be cyclic. It's when you get to n equals 4 that you get 2 non-isomorphic groups. Z4 is one of them, up to isomorphism. In other words, cyclic of order 4, but there are non-cyclic groups of order 4. We've seen examples, I think, like U10, U12, I think those are examples. No, excuse me. U8 is an example of a non-cyclic group of order 4. U8 had elements 1, 3, 5, and 7 under multiplication mod 8. All the non-identity elements have order 2. 3 squared is 9, mod 8 is 1. 5 squared is 25, mod 8 is 1. 7 squared is 49, mod 8 is 1. It's a non-cyclic group of order 4. There are, and in fact, you can prove up to isomorphism, there are 2 groups of order 4. The cyclic one and the non-cyclic one. What about order 5? Actually, I did mention this in one of the lectures. How many groups up to isomorphism are there of order 5? Or 7, or 11, or 13, or 17, or 19, or 23? What's common about all those numbers? What? They're prime. Remember what I said in one of the lectures? Got a prime order group. How many possible isomorphism classes are there? Be sure, because I didn't watch the entire lectures, but I noticed in one of the titles, groups of order P, where P is prime, must be cyclic. If P is prime, and the order of G equals P, then G is cyclic, which really means G is isomorphic to ZP. The operation of G could be lots of different things. It could be addition, it could be multiplication. The elements of G could be matrices for all we know. Under multiplication, maybe one of those general linear groups, maybe. If it's prime order, it's got to be cyclic. It's got to be isomorphic to ZP. That's really our first initial classification fact. Or I'll call it foundational. I can spell foundational classification fact. Is this fact right here. Right, I said a few weeks ago, we're kind of like zoologists. Zoologists study the animals in the animal kingdom. Algebraists study groups or later on rings and fields and try to classify them. That's what makes the subject, that's what holds interest for people in the subject. It's amazing how just starting with the definition of a group, the basic definition, you can prove all these classification facts, and this is the most foundational one. Based on the order of a finite group, if it's prime, it's got to be cyclic. There's only one group up to isomorphism for each prime. And yeah, odd G is a group. Given any group G, given any group capital G, the set of all automorphisms of G, isomorphisms from G to itself, is a group, though you should add a little bit more. You should say under function composition. The theorem. Is it difficult to prove? It's not the easiest proof in the world. Let's talk about the idea of the proof. Not all the complete details. First of all, is it closed under function composition? Closure does need to be verified. But closure is fairly easy to verify. If phi and psi are in odd G, does that mean their composition phi psi is an odd G? I'll put a question mark here. It's not completely obvious. You can't just say clearly. You should refer to something that we've talked about already, or try to prove that something from scratch. Well, certainly, you can say certainly in that this function maps G to itself. Kind of like you're going around in circles. Psi goes like this, and then phi goes back here, and the composition does map G to itself. Is it one-to-one and onto? Yep. Back in chapter 0, first homework assignment, we looked at if you compose two one-to-one and onto functions, you get a one-to-one and onto function. Is it operation preserving? I didn't prove such a thing was operation preserving, but we did mention it before. It's not difficult to prove. The key calculation would look like this, using the fact that psi is operation preserving, and then using the fact that phi is operation preserving. That's the key thing to verify. Identity. What do you think is the identity? I was talking about it just 10 minutes ago for an example. What function is the identity in this group? Yeah, the identity mapping that maps everything to itself, which I've been calling ID. I'll use the circle notation for function composition here because otherwise it looks a little weird. ID compose phi equals phi compose ID equals phi for all automorphisms. If we're going to be more consistent with the book, maybe we call this epsilon instead. It's more typically what the book calls the identity mapping. It is equivalent to the identity permutation when we're talking about permutation groups. Permutation groups are groups of functions. Permutations themselves are not automorphisms. They're just one-to-one and onto functions from the set to itself. The set may not even be a group. It could be just a group of people. I emphasized that before, for example. Inverses. Well, okay, I forgot about associativity. Probably should have put that up there. That's obvious because function composition is always associative. We did verify that either in here or in one of the lectures. I verified associativity for function composition. But here, I'll just say function composition is always associative. And then inverses. Given an element of aught of G, what is its inverse? It's got to be its inverse function. That's the only possibility. It definitely has an inverse function because it's one-to-one and onto. Is that inverse function an automorphism? Well, it certainly maps G to itself. The only thing to verify is its operation preserver. I'll put a question mark here. Does phi of A inverse AB equal question mark phi inverse of A times phi inverse of B? And yeah, as always here, you got to use what you're assuming. We'd have to use the fact that phi is assumed to be operation preserving. And phi and phi inverse are inverse functions. Phi of phi inverse of AB, by definition, is AB. And phi of phi inverse of A, phi inverse of B, since phi is operation preserving, phi is OP, I can write that as phi of phi inverse of A times, this is an element of G, times phi of phi inverse of B. But by definition, that's A times B. Therefore, phi inverse is operation preserving because phi is one-to-one. These two are the same. Therefore, these two things that I'm underlying must be the same since phi is one-to-one. why are we doing this stuff? Why are we considering groups of automorphisms? Well, for one thing, because we can. It's a natural thing to think about. For another thing, it's possible that learning about automorphisms of G could tell us more about G itself. That's possible. That's the overarching meta theme, is that maybe we can understand a group by understanding its group of automorphisms. Maybe. Or maybe thought of another way. Well, here's a theorem. If G is isomorphic to, call it G bar, that implies aught of G is isomorphic to aught of G bar. That should seem fairly natural that that would probably be the case. And so that means the contrapositive of this also is true. If aught of G is not isomorphic to aught of G bar, that would mean G and G bar themselves are not isomorphic. So maybe that's a more useful application of this concept. You're wondering whether two groups, G and G bar, are isomorphic. If you can somehow compute aught of G and aught of G bar, and those are not isomorphic, that would mean G and G bar themselves are not isomorphic. And yeah, that is an application, a common application of the group of automorphisms. Sometimes the group of automorphisms is simpler than the group itself. Maybe it has fewer elements, for example. That's certainly the case. Where did I put it? Oh, here it is. That's certainly the case here. UN always has fewer elements than Zn. If n is prime, it's going to have n minus 1 elements. Its maximum number of elements when n is prime. But Zn always has n elements, 0 through n minus 1. So the group of automorphisms of any group, well, this group in particular, is another group. It's isomorphic to another group with fewer elements than the original group. So maybe it's simpler than the original group. Maybe, maybe not. I mean, you could argue in general, UN is not simpler than Zn. Because, for example, Zn is always cyclic, but UN may not be, like this one's not cyclic. But at least it has fewer elements. Is this difficult to prove? Would I ever have you prove this? Well, I think it's a possibility. We're about out of time here. How would you prove something like this? Well, given an isomorphism from G to G bar, the question is, can you find an isomorphism from aught of G to aught of G bar? Does there exist question mark in ISO? I don't know what to call it. Should I call it psi? Maybe I should call. Okay, I'll call it psi. From aught of G to aught of G bar. So you'd have to ask, what does psi map in this group to something in this group? Yeah, the notation is getting funny. Given an alpha in aught of G, what is psi of alpha? And instead of just answering that question, I'll let you think about it before Friday's class. Hoping you want to make something in aught of G bar here. And then you'd want to show that however you define this, it's an isomorphism. There's only sort of like one natural thing to pick. I'll let you think about that. See you on Friday.